Okay, hi, welcome. This is our 3:30 press conference, ZAP, the weird green lightning from Chaiten Volcano. And this is Arthur Few, Professor Emeritus of Physics and Astronomy at Rice University in Houston, Texas. And the images that he's going to be showing, we have one image, one spectacular high-resolution image that's available with a limited license in our virtual press room in the Media Center. And that's about it. Take it away.
Good afternoon, I'm Arthur. I've never been to a press conference before, so it's my first attempt at this. But anyway, I'd like to tell you a story about this green lightning. I have a few slides, but there are more pictures on the poster than I would be showing you here. So this is the green lightning, of course, is on the right-hand side. And has anybody in here ever seen green lightning? I would be very surprised if you had. It's a very special type of lightning flash, according to my interpretation. And it probably occurs in all lightning thunderstorms. But when it occurs in a thunderstorm, it's inside the cloud, so you never see it. Now this is a volcano cloud, the plume of a volcano, and because of the structure of charges in a volcano cloud, this green lightning is coming out on the surface of the cloud, and I'll explain why it comes down on the surface of the cloud shortly. But let's go through the slides. So this is one of the two green lightning flashes that are on the poster. The structure of this cloud, basically we have up here at the top, this is the towering plume coming out of the volcano, which is down here, and this white cloud up here is the outflow from this plume going up. And this is ordinary lightning. I mean, we're getting negative lightning discharges to ground from the plume, from the outflow from the volcano. The tropopause is probably right along in here, so it's a real tall column, and these white discharges are all negative discharges. But look at this mess. I mean, this whole network of discharges in this volcano. What is obvious is that these are negative discharges going to the bottom of the plume, which means the bottom of the plume down here is positively charged. And again, this edge of the volcanic cloud is negatively charged. Now, as soon as I saw this green lightning, the first thing that came to my mind is what else in the atmosphere do we have that's green? And obviously the green aurora is green, and let me tell you a little bit about how the structure of this works. This is an auroral arc, and it looks like it's tilted, but that's just a perspective because this bottom part of the arc here is at 100 kilometers altitude all the way around. But since we're looking at it, it looks like it's tilted. This is much further away. This is closest to the camera and so forth. So this is the green aurora, and the bottom of the green aurora occurs around 100 kilometers. Sometimes, if it's a very intense electron precipitation event coming out of the magnetosphere, it will go down below this 100 kilometers and turn whitish. And if you look up here, you'll see that it's at the top of the green aurora is a red aurora. So we have these three colors. The white has the highest density, the green has the medium density, and the red has the lowest density. So we have this series of colors. All the colors are being produced by excited oxygen atoms. Now this one, well, it doesn't show up very much on the projection, but in the center of this, the photographer arranged it to catch the Milky Way. So it's a great photograph, a prize-winning photograph where we have the green aurora with a little red and a little white, and in the middle of this whole thing is the Milky Way. So that's on the poster, and it shows up better on the poster. Now, I got started on this green theme, and we've had 2 comets recently. This top one is Comet Lovejoy, and the lower one is Comet Ison. And if you'll notice, oops, they're white in the center where it's most dense. The gas is coming off the comet, surrounded by green, which is less dense, and then a reddish tail coming out of the back of the comet. So once again, we have this sequence of white, green, and red in a comet like we saw in the Aurora. And then the next one is getting even more weird. These are the Perseid meteor shower over China, and almost all of them are green. And these are going green to white to reddish white. But that's a thermal emission when it does that with a meteor, as opposed to being a chemical, oxygen radiation. Anyway, I got into this quite by accident when I was doing research on volcanic lightning, and I ran across one of these green lightning channels. And I asked myself, well, my goodness, where'd that come from? And why don't we see it with thunderstorms? And I'll get to that answer shortly, but let me show you the last slide. It's a quote from Isaac Asimov: "The most exciting phrase to hear in science, the one that heralds new discoveries, is not eureka, but that's funny." I just love that. Anyway, that's sort of the situation I felt myself in when I saw this first green lightning flash. And then I found another one from the same volcano. And then the question was, why does it occur in volcanoes but not in thunderstorms? And the quick answer to that is, in a thunderstorm, the charge is stored inside the cloud on ice crystals. And in these volcanoes, a lot of the charge resides on the surface because the ash coming out is charged when it leaves the volcano, so it can make it to the surface. Volcanoes also have ice in them. Volcanic clouds have ice, so you do get the regular type of lightning that we saw, the white part of lightning flashes. Well, my hypothesis, working hypothesis, is that these the green ones are actually streamers. And let me explain what a streamer is. The negative cloud-to-ground lightning flashes that we saw, the white ones, they're bringing negative charge to the ground most of the time, or to a positive charge center. But where do the electrons come from that participate in that discharge? And the classical description of the process is there's something called a streamer, and it goes by different names, but it's doing a lot of work. The streamer is a positive channel, and it's propagating into the cloud looking for negative centers. It's being pulled toward a negative charge center, and then the negative charges collapse onto or rain down onto this positive channel. The channel takes that negative charge that it collects and sends it to a negative discharge going to ground or something like that. So the positive streamer is the supply side that collects the negative charge that produces the lightning flash. And we see the negative lightning flash, but we rarely see that positive streamer because it's inside the cloud. But it is being revealed when we look at the volcanic lightning. So anyway, that is, I hope, a description of my interpretation of the green lightning, and I'm open to questions.
Larry O'Hanlon. So is it the same, is it oxygen involved as well? Is it the same excitation going on?
In the Aurora, you've got energetic electrons streaming down through the atmosphere and exciting the oxygen atoms. In the green lightning, you've got electrons streaming down onto the channel and doing basically the same physics of excitation and de-excitation.
Norm Sperling, it's been a long time since I looked that up, but I thought the Aurora line was the 5007 angstrom line of very rarefied oxygen, and it needed to be that rarefied to emit the light. The lightning that you're showing is anything but that rarefied. How do you get the same color out of a very, very different situation?
Well, you're right about needing the low density because but think now the channel creates a shock wave when it goes through the atmosphere and evacuates the channel, and it remains, as long as it remains conducting, it remains hot and low density. So it's doing the same physics.
I think we have a question from the chat.
Yes, this is a question from Rachel Berkowitz from Physics Today. And her question is, we don't see green lightning in the atmosphere, but were the conditions at Chaiten so unique that you'd be surprised to see green lightning at another volcano?
These are the only two channels I've found so far, and both from the same volcano. Does that answer the question?
Any other questions?
Hi, I'm Irene Klotz. When was that taken, and was that the first time that green lightning's ever been photographed?
I cannot answer that second part. It's the only one I've found, but I haven't. I wasn't looking for it, in fact. I was just looking for lightning. That was done, let me see, it's on the poster. It was 2011, something like that? What?
May 2008.
2008.
Thanks.
Any others? Any in the chat? No. All right, thank you.